In looking at wind energy, my specific area of research is a CFD design and aerodynamic optimization of wind turbine rotor blades for small-scale wind farms, and specifically within the Caribbean tropical environment. This research was preceded by earlier research. We looked at the development of an implementation model for wind farms and wind energy in the Caribbean. This investigation and research involved the study of the technology options, configurations, and the economics involved. We looked at the load profiles, the availability of the renewable energy resources, component costs, technology alternatives, and the economic constraints involved. The motivation for this research lies in the fact that the Caribbean has a dire need for alternative energy resources. We need to reduce the dependence on fossil fuels, reduce the high level of fuel imports. It allows for energy and economic diversification. It's job creation and new employment, and it allows the Caribbean to meet its international commitments for climate change. It is estimated that the Caribbean can derive at least 20% of its energy resources from wind. Following on from that earlier research, we realised there's a new opening and a new area to look at, which hadn't been studied in much detail. That is for small-scale wind farms and microturbines within the urban environment. This is looking at the identification of preliminary designs and the development of an aerodynamic performance prediction tool capable of analysing a range of different wind turbine blade profiles. Now, the Caribbean is on its way to the development of wind farms in general. We've passed the stage where there's data collection, adequate data exists. Sites have already been selected, environmental analysis has been done, and the capital and financing has been identified. We're now at the stage where we have to look at proper selection of wind turbines, not just in capacity, but specifically in their performance and how they perform under Caribbean conditions. When we're talking about small-scale wind farms, we're talking about medium wind turbines in a range of 50 kilowatts to less than 1 megawatt. These have the advantages of that. They have proven energy yield, an improved energy yield, flexibility of placement, I spelled that wrong, I've pronounced it wrong. That's meant to be placement. Reduced downtime and increased availability. The advantage here is that you can take, instead of taking a 1 megawatt wind turbine, placing it on a site where its performance is limited to the wind profile at that specific site. You could take 20, 50 kilowatt medium-sized wind turbines placed around a wider area, which could then take advantage of all the different wind profiles around that wider area. In that way, if you have a reducing wind speed and downtime of the turbine at one specific point, you can then be generating energy from other wind turbines further away. When looking at microturbines and small wind turbines, we're talking about small scale in the region of less than 50 kilowatts, and micro in the region of 100 watts to 3 kilowatts. The advantage we have here is that they have commercial applications, domestic applications. They're available for demand-side energy reduction. They have grid time potential, and they're available on-site, close to where the energy is needed. Now, there's a deliberate and specific need in the wind energy industry for further data where small wind farms and microturbines are concerned. The existing and available data is usually associated with aeronautical applications, specifically for aircraft design and their wings in particular. Now, aircrafts tend to operate under steady flow conditions where we have low turbulence and low angles of attack. For small wind farms, they operate in the lower atmospheric turbulence. Microturbines operating in the urban environment tend to experience severe unsteady flow conditions. The wind industry specifically needs designs for wind turbines which reflect their true operating environment. If we look at the components of a wind turbine, we have our rotor, gearbox, generator, and the power electronics side. Where the rotor is concerned, the conversion of energy from wind energy is aerodynamic. It's converted into rotational energy. That moves on to the gearbox, which is mechanical, and we then move on to the transmission, which is electrical. In designing wind turbine systems, the gearbox, generator, and power electronics are separate areas of research. Where the rotor is concerned, this is the area that we'll be concentrating on. This is the area that we feel is specific to the Caribbean. In wind turbine design, the power production is limited by the range of operational speeds, and design and efficiency improvements need to maximize this operational range. If we look at a basic plot of wind speed against power, you'll see that from no wind speed, the wind speed increases the power output according to the power formula. The wind speed increases power by the cube of the wind, basically. What we are looking to do for the Caribbean is to take a standard turbine and increase the efficiency closer to the left, where we have greater power being generated at lower wind speeds. The factors involved in the design of a new turbine blade will be the aerodynamic response of the wind turbine, its Betz limit, which is the theoretical maximum power available from the wind, and the turbine efficiency. Again, if we note that the efficiency of a wind turbine is determined by the rotor efficiency, the generator efficiency, and the transmission, we are concentrating on the rotor, efficiency of the rotor. That's what we're looking to increase. The efficiency of the rotor and the power produced by the rotor is also affected by the climate under which it operates, and in this case, the density. The Betz limit tells us that 60% of the available wind energy could be converted into useful power. Now, with a 70% efficiency rate for wind turbines and a maximum efficiency available of 60%, we have a reduction to more or less 40% of the available wind power. So in designing a new turbine, what we're looking to do is move this efficiency curve closer to the theoretical maximum limit of 60%. For any given wind speed, in airfoil design, wind turbine blade design, density is a very important factor. Most wind turbines are designed for the northern hemispheric atmospheric conditions, where we have cold, high density air conditions. In the Caribbean, we have a much lower density, and this itself translates to the performance of the wind turbine. If you take a turbine designed for northern conditions and put it into the Caribbean, you would not get the same performance as you'd expect. High density gives us higher pressure and higher lift on the airfoil blades. Lower density gives us lower pressure and lower lift. What we're aiming to do is increase the aerodynamic lift force under Caribbean conditions. Caribbean air density also has another important factor. This is the fact that it is diurnal. This means that we observe high values during the night and low values during the day. There's also density fluctuations, where we have a seasonal effect. High densities are observed during the early months of the year and low densities in the later months. This tells us that precise wind power density calculations are required, specifically for day and night density changes. Where density and power output is concerned, if we use assumed air density values, this leads us to either an under or overestimation of the energy production. Accurate energy production estimates require the actual density at the specific site that you are utilizing. It has been noted by many researchers that the application of accurate air density data in wind turbine power production can decrease the potential error by up to 16%. When we look at small wind turbines operating in the urban environment, the unsteady conditions lead to large changes in angle of attack, sudden large gusts, changes in wind direction, and an unsteady weight shift from surrounding buildings and towers. This leads to impulsive loading changes and dynamic stall of the turbine. These are the common types of wind turbines that most people would recognize. We have the Savonius vertical axis turbine, the most common three-bladed system that most people would certainly recognize, and the Darius vertical axis turbine. Both have their advantages and disadvantages. I am concentrating on the three-bladed system. It's the most common in use today, and it happens to be the most efficient and the most practicable. Other systems have not been proven as yet. Three-bladed system is proven for energy production. For blade turbine, wind turbine blade design and efficiency improvements, we have to aim to increase the annual energy production and increase the power curve. Standard three-bladed system that we are looking at, compared to other systems, needs to improve closer again, as we mentioned earlier, towards the theoretical maximum limit of 59%. Other systems that might give you better energy production also have to operate at higher speeds. Where wind speed is of an important factor, and energy production in particular, we want to ensure that wind energy can be converted at the lowest possible speeds moving up. The most important factor for three-bladed wind turbines is the lift that they produce across their sections. In designing a new turbine, what we are aiming to do is increase the lift force and reduce the drag. The lift force and the drag are not only determined by the wind speed available, but also by the profile of the section that's been selected. The software that we'll be using to design this new airfoil will be Xfoil. This is a freeware. It gives us the basic parameters of lift and drag. It gives us our airfoil coordinates, which can be manipulated, and it's a basic airfoil design and analysis program. For tropical airfoil, the requirements are to try and achieve a strong suction peak on the upper surface and a high pressure region on the lower surface. We'll be manipulating the angle of attack, chord length, solidity, and the camber, and also looking at the effects of twist. For the wind turbine design optimization model, our inputs will be the regional speeds, Y-ball parameters, fixed or variable speed, lift and drag coefficients at each wind speed. And our outputs are expected to be the optimal aerodynamic profile. Now, computational fluid dynamics is probably it's still at its early stages where wind turbines are concerned. It's usually used in other fields, but it gives us visualization of the flow around an airfoil, and it's a useful tool in designing new airfoils. Typical components of a CFD code will be the mathematical model, compressibility and incompressibility effects, the input of equations, turbulence modeling, our solution method, and it gives us a computational grid to be analyzed. With CFD, we're able to compute the 2D steady flow effects, 3D turbulent flow effects, rotational effects, the aerodynamic force, and coefficients. We'll be looking firstly at the 2D model. This allows us to map the airfoil section and its mesh, gives us computations for the coefficients of lift, drag, and moments, gives us airfoil design and optimization, which is what we're looking for, flow modeling and visualization, so we can see what's actually happening around the airfoil, solves the necessary flow equations, and gives us a graphical representation to analyze. The CFD numerical model is to discretize the fluid domain, establish the field variables at each node of the grid, and relate the differential equations to the field. Now, there are several different types of turbulence model that are used in CFD. All have different outputs and different usefulness. We're looking specifically at the K epsilon model. The results for these different models vary, but it gives us and what we're trying to do is look at the standard airfoils that manufacturers produce and compare it to a Caribbean-specific model. So for those purposes, we can get a direct comparison between the standard and optimized airfoils. So we've selected the standard KE model, which is the most commonly applied model. It allows for two transport equation model solving. It's suitable for initial iterations, and it allows for parametric studies. Now, moving forward from this research, proposed work going forward will be software selection and familiarization. The most common software used in the wind turbine industry is Fluent, CFD. The software that will be used for work going forward will be dependent on the university and what's actually available. We'll also be refining the aerodynamic models, integration of the airfoil profiles into CFD software, grid generation for selected profiles, and integration of the wind speed data into CFD software. This will be followed obviously by the analysis and interpretation of the results. The expected results for Caribbean wind turbine using CFD design and optimization will be correct wind turbine sizing and profile selection for tropical conditions, improved power production curves for tropical climates, significant energy conversion and efficiency gains, an overall increase in annual energy production, and a defined tropical rotor blade geometry and characteristics. We'll then be able to compare different rotors under the same conditions, which is ultimately what we need. We need a rotor that acts specifically under Caribbean conditions, rather than taking a standard manufacturer's rotor blade, which is designed for a certain wind speed. We need rotor systems that act under the environmental conditions operating in the Caribbean. The implications of this research is that we'll be able to produce specialized airfoil sections. Our energy capture will be optimized. We can produce a regional catalogue of airfoil shapes and categorize all wind turbines for the region. This also has implications for the Trinidad and Tobago government, whose intended investment into wind energy is fairly imminent. It will give them reduced financial exposure, increased financial returns, and increased energy production. It's also important for regional governments who are seeking to reduce their dependence on fossil fuels, and particularly the fossil fuel imports. And it's available for rollout throughout the CARICOM region. That concludes my presentation. I hope you found it interesting.
Thank you. I'm just going to... First, I'm going to try to summarize what you said about upper energy as a people, because it's most technical. The research is focusing on design efficient wind turbines, which are suitable for the environment, the CARICOM and Trinidad and Tobago, and try to maximize the utilization of energy capture and efficiency by looking at the fact that the air density, which is a parameter in situation, vary depending on altitude, winter, summer, seasonal, and so on. And he compared the different types of turbines. Some of them he came to the conclusion that the CP8 turbine model is the most efficient. And you are only focusing, as I understand, on a small scale, which range from 3 kilowatt to 50 kilowatt, which I call the residential, commercial, small scale application, which is really nobody's caring about the design for it, because everybody is designing a larger scale. And you mentioned that the CP8 turbine, so I'm asking now two questions. The first one is, you are looking for the best shape of the aerofoil, which is supposed to match the environmental conditions, and we try to maximize utilization factor CP by trying to have near maximum CP, which is the best design. But it's known fact is that CP in most of the application cannot exceed 30.35 to 0.38. So no matter what the design will be, will always be limited by the practical commercial design of a CP, which is about 0.38, which is far less than 0.59. So the question is that, do you think that you can exceed the existing, most of the turbines in the world have a CP factor of about 0.35, maybe 0.4. And you claim that you can do it and push it all the way to 0.59, which is, nobody can do it.
I'm not claiming that I can push up to the maximum value of 0.59. What I'm suggesting is that the wind turbine industry, most of the developments are concentrated in the northern hemisphere. The conditions under which they operate, for which they're designed, are high density, low temperature conditions where you get higher pressure and higher energy production from these particular turbines, these large scale turbines. What I'm suggesting is the conditions that we have in the in tropical regions, the Caribbean in particular, we have a lower density, higher temperatures, seasonal effects, diurnal effects. These all combined reduce the efficiency of the turbine. As you said, if it's 40% odd in the rest of the world, it's likely to take the same turbine and place it under Caribbean conditions. It's likely to be less. So what we're looking to do is push that efficiency up. Maybe the graph I put was a bit misleading, but the point is it's about increasing efficiency.
Okay, so the second question now is, you mentioned that the best design is the CP design, but this is true for large scale. Some people now are claiming that Darius and vertical axis wind turbine is the most suitable for small scale application from few kilowatt up to 100. And in Canada, I come from Canada, where most of the research in hydropower is dealing with Darius and vertical axis because they claim that in the midstream up to the 600 kilowatt, and that has to be more efficient and suitable for any wind regime. You didn't mention anything about the wind regime, because the wind regime will determine which turbine model you are using, whether cut in, cut out speed or so on. So if you can maybe elaborate that, what is the wind regime in the data individual, and what is the best design, and what cut in and cut out speeds you are looking at?
Well, the direct designs that you're referring to would be useful in the urban environment. There has not been a large-scale system as yet that's been designed that is efficient enough to produce large-scale power. These would be limited to maybe domestic applications. But even still, at that level, it's still under investigation, it's still unproven. Three-bladed design is proven technology.
Because the technology is mature and everybody
Yes.
Okay, thank you.
Thank you very much.